Okay, we're gonna resume this foundation design. So, based upon current design display shows slab design. Right, this is slab design, which is MET. There are two methods: design-based finite element method and stream method. So, finite element method and the stream method basically is based upon finite element analysis, right? And then the only difference is the way to how to show the forces. Since we are using moment and shear, most likely forces, I think we're more familiar with to play with the shear force and moment instead of just stress, right? Even though stress, basically, when you collect all stress multiplied by the associated cross section area, you can make the resultant forces in shear and bending moment. So I'm gonna show you then how to define the design strip, and then show you how to collect the strip forces in shear and moment. So visually more is understandable. So I'm gonna unlock. So what we're gonna do, so here I think you should supposed to take some class about two-way slab design. In there, in ACI 318, we have equivalent frame method, which is pretty much similar the way. So what we're gonna do here, we're gonna click design. We're gonna define the design strip. We're gonna just keep it a strip level, slip layer A is in Y direction, but for speed up, I'm gonna just assume maybe 5 or 10 10 feet on the left and 10 feet. So we're gonna use a 20 feet wide design strip. So I define the left and right for design strip. I'm gonna click here and click there, right? You see that purple line? For the checkbox, you can turn on that design strip width graphically. So let's see where is the design strip. So design strip, okay, show width, right? Design strip object, show width. Oh, this is inches. Okay, I have to redo this. It should be fit. So go back. What? Can I do the undo? Okay, select that. I delete the design strip again. I'm gonna change to unit to fit, right? And design strip, I'm gonna use 10. I'm gonna copy and paste. Okay, and click here and click there. So you see that design strip, right? Is there a better way? Show width station. Yeah, somehow they changed showing the entire solid. Okay, used to be a hatch, but anyway. So, but we need this design strip. Select this. We need to replicate over. So we're gonna copy, replicate Y direction, right? But increment because of 20 feet Y width. So maybe what, 5, 6, 7. Let's say. Let's try 6. So I cover all this our mat. See that design strip is defined and placed in this and cover all the entire mat width. Alright, what we're gonna do another design strip. Define the design strip. Same thing, 10, so 20 feet wide. But now this time we're gonna do Y direction. So click the Y design script and copy. Replicate. This time I need to copy it over to in an X direction. This one maybe I need to do maybe 7. Yeah, probably I need to copy one more here, one over here. right? So it seems like I cover all. See that this design strip, it will cover entire over the mat. The reason why is the design strip will convert all the design stress based upon each load, right, and create the resultant forces. So this is actually two-way. Because of mat is a two-way, we normally use and two design strip, one in the X direction and the other one is in Y direction. So just define the design strip. We're going to run that analysis. I will show you the design forces in shear and moment for each load combination. Okay, same finite element analysis, but we should be able to see the forces. So I'm gonna click here and I'm gonna turn up the design strip graphically. Okay, turn up. What do you see there? Purple line representing design strip. Go to display this time, and then here show forces. Instead of we are looking at stress, we're gonna check strip force, right? So strip force. Okay, load combination S2 is 1.2 plus 1.6 libra. So you want to see first the shear forces. Alright, so what you see, the shear forces based upon 1.2 dead load plus 1.6 libra, right? Now it looks something that you're familiar with, right? Because this is continuous spring, instead of just one, two support on one each ends, we have a continuous spring. So this is something like equivalent continuous beam supported by continuous spring. That's why what you see, the spring constant, right? Some design forces, you could see that along the design strip near at the column has a relatively big moment shears forces. Absolutely, that near at our wall, you see that much bigger shears forces, right? Same as obviously we saw the biggest shear stress, which is shear stress multiplied by whatever just the design strip width and depth. You can calculate the shear force. So this is something shear force diagram in X direction, but if you want to see the Y direction, you can turn on, look at it, right? Shear force diagram in Y direction as well. If you want to show both. So it's something that you need to verify that whether your model is something working reasonably or not. Similar to shear force, let's check the moment in Y direction, right? If you want to turn on the value on the diagram, turn on, right? You could see. So maybe you can just show this diagram on your report or PowerPoint, something that you follow along each procedure and one by one and verify so that you can learn instead of just jump on right away to design. This is something validation again. Your model, when you create it, you should be able to check one step at a time and make sure everything looks reasonable. If you want to check something with Dello plus something wind effect, you could see this, right?
So
something
my best
like
friend threw
that.
me a surprise party.
But you need to make
I was
sure the
so not expecting
magnitudes
it. Also wasn't
unit.
expecting this red
So
patch
this
to show
is
up on my
something
neck.
generally
My plaque
all
psoriasis doesn't
about
always
how
feel
the
like a big
design
deal,
strip
but
works.
my idea of a party does not
Finite
include
element
fancy red
software
patches.
usually use
Now for clearer skin, I choose
strain,
Otezla.
right?
Otezla
I'm
apremilast
not
is a
sure you guys
prescription
are
medicine
familiar with
used
the
to treat adult
metrics, but
patients with plaque
I think
psoriasis.
initially
No
finite
other
element
therapy or
software
systemic therapy
calculate
is appropriate. Otezla can help you
one
get clear
the
skin after just 4 months. Don't
multiple
use Otezla if you're
equation
allergic to it. Serious allergic reactions can happen. Get
analysis
medical help right away if you
to
have trouble
find out
breathing or
strain.
swallowing, swelling of the face,
Then using
lips,
strain
tongue, throat,
multiplied by
or lungs. Otezla
young
may cause
modulus,
severe
obviously you
diarrhea,
can
nausea, or
calculate
vomiting. Tell
stress.
your doctor if these occur. Some
So
people
where
taking Otezla have
any
depression,
stress
suicidal
is
thoughts, or weight loss.
you
Tell your
find,
doctor if you have a history of depression
you should
or
be able
suicidal
to
thoughts,
see
or if these
is
feelings
it
occur. Upper
tension
respiratory
force
tract
or
infection and
compression
headache may
stress
occur.
tension stress or compressions or shear, something like that, right? It depends on the stress components and associate the relevant cross-section area modification. You could calculate either shear force or moment or actual compression and tension forces. So something that is part of the procedure how to calculate the resultant force using stress. All right, so I think the last one I'm gonna just turn off that. So we're gonna use same thing, and let's check the shows slab design, right? The previously we used finite element base, so now this time I'm gonna switch to strip method, right? So here I still keep the minimum reinforcement, but first I'm gonna show you bottom bar. There are many ways to do this. You want to show the area per unit, or let's take a look at it first. You see also diagram show the area of, this is fit, so let's change to inches, right? So in inch means I need to change again. So here, okay, did I change the unit? Okay. Okay. Let me just go somehow unit display, show design, bottom bar, show bottom bar. Okay, here it is. Oh, this is inches square per inches. That's why this number seems pretty small. But obviously you need to multiply by the 20 feet, right? Times 12. So that is the total number of area of steel. So you can use the intensity, right? Or inches square per inches, unit inches, this is. Or I'll just use the show number of bar instead of number of bar area, because we have data. So save can show this directly based upon the rebar I selected. So I'm gonna choose show number of bar, right? But here typical bar, instead of the playing with all, I'll just assume that you know what, I'm gonna use number 11 bar as a maximum bar, right? And spacing 12. So whatever, just this is typical bar, I'm gonna place in X direction and Y direction, top and bottom bar first, and then this is the typical bar mets. But what the bar you see on top of this is additional bar. Seems like we have a quite significant amount of additional bar we need to place at some middle of mat and the column, and then under the concrete wall, right? So because this is something designed now, you need to really consider constructabilities as well as just engineering how to organize this data, so that construction is more reasonably doable, right? So we usually play around a little bit, because this is only the tool SAFE can have it, but it maybe can play around. Instead of using number 11 and 12 inches, we can use 6 inches. So you see the most of area number 11 and 6 inches it will cover, and still we have some additional bar on the side of the core, which I think you could see this is number 11 at 6 inch on center, or two bar number 11 bundle at 12 inch on center, which is same area of steel, right? So this is something that you can play around, what is all engineering judgment, how to place the rebar more reasonable way for better construction. Now still we have a lot of additional bar to win it somehow, because this makes sense, because we have the concrete wall carry a lot of gravity and lateral load, so typically you'll see more heavy bending moment and shear under the wall. So at the end, we may end up with a multiple layer of rebar, because you think this is almost, what, 96 inches mat. It's almost one floor thick mat, right? Probably end up with a couple of layers, right? X, Y direction. I've been designing the wall, probably 2 layers in each direction is pretty common, sometimes 3 layers. Bottom bar in X direction, another 3 layers in Y direction. Still, this thickness is very huge. We are talking about, right, the mat foundation, almost 96 inches for a 40-story building. Sometimes even much bigger, almost 10 feet or 11, 12 feet. Think about the 600-meter tall building. So we need to do some iterations, right? What will be the most kind of reasonable typical bar, either number 11-12 or number 11-6, means either you could say number 11-6 inch on spacing, or you can interpret, I'm going to place 2 number 11, which is a bundle, 12 inch on center. So engineering judgment is something we need to bring this, our constructability's understanding, so we can find a more reasonable or appropriate layout of the bar. So here I show you the bottom bar, but you can turn on both and then X, Y, but visually it's quite hard, so I just turn on and off. So I usually prefer to print the bottom bar in one direction and separately, and Y direction, right? And also now later on top bar and X directions, which I think top bar and X direction we probably don't need too many. So I'm gonna increase the spacing, maybe 10 inches. We still have a few, maybe 8 inches. It seems like, yeah, number 11, 8 inches. But this is my model. Your model obviously has a different condition, so you need to play around which number of bar and spacing makes sense, right? So you could do the and a Y direction as well. Obviously, Y direction, again, you have more overturning moment due to the wind loads, right? And then has more significant bending. Obviously, bar design is based upon your bending moment, maximum bending moment. So you could just see and choose. So you just play around this. I want you to just kind of show, right? Something like that. If you want to show sig, I want you to just play around and choose the one option that and include this snapshot in your report. So you can just play around each bottom bar X direction, bottom bar Y direction, top bar X, top bar Y. So this is how we designed the rebar board. But basically, I want you to understand the same method, nothing different. Same as your spread footing design, right? Just look back, open your foundation design book, and see how you design the footings. Basically, based upon column load, divide by your footing area, right? Then you can convert your soil stress, right? Column reaction divided by the footing area make soil stress. This stress, soil bearing is pushing uniformly, so the footing will experience cantilever bending moment, right? So that you could just checking the shear stress and shear capacity, and also bending using bending moment for your rebar design. So just I want you to just see more globally, even though this is a huge scale, but nothing different. So you need to exercise this. Hopefully, I think every team should get your model ready up to this level by next week. So we have only a few weeks left, right? Thanks to tomorrow, I'm sure your team's gonna finish your 3D model, right? And if you didn't finish it within 1 hour, just do some iteration and finish your 3D model, and then convert to the .f2k file, transport the data to the safe, and start creating the safe foundation model. Just follow along, just one at a time, right? I think everybody could finish this by tomorrow, but if you're not, don't just wait. You're not gonna finish it. Do not push it to the next week. Just let's get this done at least, right? So basically I'm gonna give you just recap here what we did, right? We're using 3D ETABS model. After analysis, we export all the reaction, column reaction, wall reaction for the all load cases and create .f2k file, which is but these reactions, obviously we are just collecting and transfer at the bottom of the column and the walls, right? So once you export it, you could open a safe software and import that file, .f2k file you just created. Just check all the loads are all transferred by open and show your load cases, which is just a verification, and follow along. We're gonna define the material properties for the mat, either 5,000, 6,000, 7,000, it's up to you, but we need to adjust the Young modulus. And then section properties for the mat, we initially assume 84 or 96 inches thick, something like that. But you need to click associate with concrete strengths, right? And then draw the mats based upon using your geometry you export. So you should have all the nodes from the ETABS is for the column and wall. So you click the outline of the mat. But since you don't have any additional geometry, maybe you can extend by certain distance. I use a 60, but something that we need to check anyway during the procedure more closely and iteratively. But just assume for something 60 inches, and choose the mat and assign the properties, thickness, right? After you finish the geometry is done, last one you need to define soil subgrade modulus, which is a soil spring. I just give it a 480 kip per cubic foot. So you're gonna select the mat and assign the boundary condition, which is soil modulus of rupture, because this is we're dealing with is area spring, similar to our point pin or fix, right? So once you are done, you can run the model and check all the load cases and set up the load combination, which is same as ETABS and any floor framing design. And adjust the concrete cover. I think somehow I couldn't find out. Maybe I'll look it up and find somehow they relocated. And run the analysis and check. First thing, you could check the soil bearing under the dead load, gravity load, right? Whether it should be less than our allowable soil bearing capacity. And you could also consider looking at and also combination of your wind lateral load, which is it allow some reduction. They could be the Win X and Win Y both, right? And check the overall deflection and check the shear, concrete shear capacity, and design the reinforcement of what I explained. So this is something general step. I want you to follow along, finish all the map foundation by tomorrow. Otherwise, end of this week, okay? If you have a question, just watch this video. Alright, this is going to be end of today's tutorial. Great. See you tomorrow.
My best friend threw me